Hi students, in this lecture I am going to discuss previous IIT problems based on the concepts till now what we have learned. See the first one, a rigid insulated wire frame in the form of a right angle triangle ABC is set in a vertical plane as shown in the figure. Two beads of equal masses m each and carrying charges Q1 Q2 are connected by a cord of length L and can slide without friction of the wires. Considering the case when the beads are stationary, determine the angle alpha, tension the cord, normal reaction on the beads. And coming to B, if the cord is now cut, what are the values of the charges for which the beads continue to remain stationary? Okay, so this is a question asked in 1978. So see diagram. So this is a wire frame, and these two are now beads. So this wire is passing through those beads. So condition is now beads are stationary. So we have to find alpha value, tension, normal reaction. And finally, when cord is cut, the values of the charges, right? Let's see how we start the problem. See diagram given. So given 30 and 60. This is now right angle 90. Now beads are these are now beads. Right. Now this is making angle here alpha, which we have to calculate. So when this is alpha, this becomes now 90 minus alpha. Right. That becomes now 90 minus alpha. Right. Okay. Now focus freebird diagram for each bead. Normal reaction, normal to that wire frame. That means this is now normal. So take it as N1, mg downwards, given equal mass set. And you can see here tension. Tension is now along the string length, and tension is always pulling force. So it is now like this tension T. Okay. And next we can see here repulsive force. So charges, take it as this is a Q1 charge and this is a Q2. Repulsive force also along the line joining them. It is now like this. So take it as F, repulsive force. So we have taken now FBD for the bead. Normal reaction, normal to this wireframe. Tension along the string length. By this charge on this charge, repulsive force. It is also along the line joining them. That is now F and mg downwards. Right. Now see for second bead. Normal reaction. So take it as N2, mg downwards. Tension is T, and repulsive force again along the string length, that is F. Right. Now since beads are in equilibrium along this along the wireframe net force must be zero. Normal to wireframe also net force must be zero. Okay. So I'm writing first equation along the wireframe. See, along the wireframe, what we can write? Along the wireframe, it is mg sine 30 should be balanced by t minus f into cos alpha. So equation 1. So this is along the wireframe. Along the wireframe, net force must be zero. So weight component must be balanced by component of tension and force which are of the wireframe. That's why it is a T minus F into cos alpha. This angle is alpha, right? Component is cos alpha. Next. Now take in the same way for this second bead, weight component, that is, so weight component mg sine 60, mg sine 60, that should be balanced by T minus F into sine alpha. See how we got this one. So this angle is 90 minus alpha, right? So T minus F into cos 90 minus alpha. That is now sine alpha, which is of the wireframe. And that is balancing now mg sine 60, right? Equation 2. Now you can see from equation 1 and 2. Let us divide equation 1 with equation 2. Divide equation 1 with equation 2. mg gets cancelled. Okay. It is now T minus F gets cancelled. Then see what we get. Tan alpha equal to root 3, right? That implies alpha equal to 60. So we got the value of alpha, right? And once we get the value of alpha, we can find out tension, right? Either by using equation 1 or equation 2. Let us say I'm taking equation 1 to find the value of a tension. So to find the value of tension from equation 1, tension equal to, from equation 1, tension equal to, see what we can write, F plus It is mg sine 30, and this is now cos 60, right? Cos 60 means 1 by 2, sine 30 1 by 2, those two gets cancel. Remaining is now f plus mg, right? It is tangent t equal to f plus mg. See carefully once. Sine 30 1 by 2, cos 60 1 by 2. So 1 by 2, 1 by 2 gets cancelled. Remaining is now mg plus f, right? If you want, you can take from second equation also. We get same. It is sine 60. This also sine 60. So sine 60 gets cancelled. So t equal to f plus mg. And here what is f? Here f value is 1 by 4 pi epsilon naught q1 q2 by L square. Okay. So that is we got the value of tension, right? From here. So next we have to calculate what is now N1 and N2. So we have to find the values of N1, N2. See how to find those values. So finding those values. To find those values, focus now force equation normal to wireframe. Okay. Normal to wireframe means, see what we can write here. N1 should be balanced by N1 should be balanced by, it is mg cos 30 plus t minus f sin alpha. Okay, equation 3. And see directly here what we can do. In the place of t minus f sin alpha, from equation 2, t minus f sin alpha, in the place of that we can write mg sin 60. Now substitute here mg sin 60. This is now mg cos 30. This is mg sin 60. That means it is equal to mg into root 3 by 2. Again mg into root 3 by 2. This becomes now root 3 mg. Okay. How means we are taking from equation 2 in the place of t minus f sin alpha. Substitute from 2 mg sin 60. Okay. Right. Now see carefully is n2. To get the value of n2, n2 value, n2 equal to mg cos 60 plus t minus f cos alpha, right? Writing net force must be 0, normal to wireframe. Okay, right, then see what we get. Again, what we can do from equation 1, in the place of t minus f cos alpha, we can write mg sin 30. Right here mg sin 30 means mg by 2, and this also mg by 2. That means n2 equal to mg. Okay, so we got the value of alpha and we got tension and the values of n1 and n2. Okay, and see last one. If a spring is cut, if a spring is cut, if beads remain in equilibrium, then their charges. Okay, if beads remains in equilibrium, right? If a string is cut. If you take either equation 1 or equation 2, let us take, I'm taking equation 1 from equation 1. See where change comes. when bead is cut, sorry, when string is cut, tension becomes zero. Therefore, mg sin 30 equal to minus f into cos 60. So cos 60 1 by 2, and this is now sin 30 1 by 2. That's cancelled. So mg equal to minus f. So and I am writing here mg, or you can say minus f equal to mg. Okay. In the place of f, what I can write here? It is minus 1 by 4 pi epsilon naught q1 q2 by L square is equal to mg. Okay. So from this, see what we get now. So we get q1 q2 equal to minus 4 pi epsilon naught mg into L square. So that minus indicates they must have opposite signs. That minus indicates they must have opposite signs. That means they have to attract each other to maintain equilibrium. Okay, right. Now see next problem. Under the influence of the Coulomb field of charge plus q, a charge minus q is moving around it in an elliptical orbit. Find out the correct statements. So this question is asked in 2009. See options once. First one, the angular momentum of the charge minus q is a constant. Linear momentum of the charge minus q is a constant. Angular velocity of the charge minus q is a constant. Linear speed of the charge minus q is constant. Right? Regarding angular momentum, linear momentum, angular velocity. Next, linear speed. Okay. See how to solve this one. First one, angular momentum. So this is possible when net torque on minus q is 0. And coming to here, if net force is 0, okay, but you can see plus q always exerting a force on minus q. That means on minus q net force is not 0. Therefore, option B is not correct. Okay. Next. And here mass of this charge is a constant. So momentum changing means here linear speed is changing because it is given elliptical orbit, right? So speed is now changing. See how we are writing equation for this. First make a diagram for this one. Plus q is fixed. Now taking here one elliptical path. This is elliptical path. Okay, like this elliptical path. Now take the path, okay, like this. If you observe carefully, let us focus now. Suppose now this is location of minus q. Okay, location of minus q. This plus q always exert a force on minus q, and that is always passing through plus q, right? So if you take a torque equation about plus Q, since the force always passing through plus Q, torque becomes zero. And we know net torque equal to it is dl bar by dt. It is dl bar by dt. Since net torque equal to zero, that implies L bar is a constant. L bar is constant. Okay. Next. So when it is moving, there is no energy loss. When there is no energy loss, if you observe carefully, electric potential energy plus kinetic energy total is now constant. Okay. Coming to potential energy, it is K into Q into minus a Q by R. Okay. This K stands for 1 by 4 pi epsilon naught, and this is kinetic energy here, Ke plus Ke. Ke means I can write here half mv square equal to constant. See, from this what we can say. Here separation between the charges is changing. So since separation changing, potential energy changes. Okay. So since the potential energy changing, kinetic energy has to change to maintain sum is a constant. Anyhow, mass is a constant, therefore speed has to change, right? And when speed changing, coming to omega, omega equal to it is v by r, right? When v changing, okay, wait, or I can do one thing here to have a convincing explanation. We can take like this for omega. We got from first one L bar is a constant. L bar means I can write here. L bar means I can write I omega per particle, that is now constant. Okay. In the place of I, what we can write? It is m r square. It is a particle, right? And r is now distance. But you can take a small r because distance keep on changing, right? Take a small r. So mr square, r is now distance of minus q from capital Q. Mr square into omega, it is a constant. Mass is a constant, r is changing. Since r is changing, omega changes. So omega is not a constant. Omega not constant, speed is not constant, right? So only thing is now it is angular momentum is a constant because net torque equal to 0, right? Okay. Now see next problem. So for this options, it is only option A is the correct one, right? Right. See next problem. 2-point charges plus Q and minus Q are held fixed at minus d comma 0 and d comma 0. Right. So one is on negative x-axis, that is positive one. And negative charge on positive x-axis. Positive one is on negative x-axis. Now electric field at all points on x-axis has same direction. Work has to be done in bringing test charge from infinity to the origin. Electric field at all points on y-axis is along x-axis. Dipole moment is along x-axis. Okay. Right now, see carefully. Positive charge is kept on x-axis. Right. Now, see how we are solving the problem. First, make a diagram for this. Let us take this is origin x equal to 0, y equal to 0. Origin. One is now at minus d comma 0. That is a positive charge. Other one d comma 0. That is a minus q. Right. Now see what happens here. He is asking regarding electric field direction. Okay. Let us focus now. If you take any point in between plus q and minus q. See, we have discussed that whenever we want to calculate strength of the field, first we have to imagine a unit positive charge at that point. So imagine anywhere in between plus q and minus q, one positive charge. If I take a positive charge, see what happens. This positive charge repels this positive charge. So direction is right side. This is negative charge attracting, and that also right side. Right? That means if you take at any point in between these two, direction of field is right side. Okay? In between plus q and minus q. Let us take now right of minus q. Where is it? Right of minus q. If I'm taking right of minus q somewhere here, I unit positive charge. See what happens? Minus q is attracting, plus q is repelling. But here attraction dominates. That means if you take any point to the right of minus q, direction of field will be along negative x-axis. Okay, right. Now come to here. If you take any point to the left of plus q, where any point to the left of plus q, imagine a unit positive charge. Now plus is repelling, minus is attracting. But here repulsion dominates. Okay, that means it is again left side. That means when you are taking any point left of plus q, right of minus q, direction of field will be, it is along negative x-axis. And if you take between the charges, it is along positive x-axis. Okay, that's why first option is not correct. Okay. Okay, now we have to focus regarding work done to bring a positive charge from infinity up to origin, up to origin. And this will be equal to charge into potential difference. So assumption is that we are bringing the charge very slowly. So when we are bringing a charge very slowly, then by external force work done is equal to change in its potential energy. Okay. Now here, bringing from infinity, right? Bringing from infinity up to origin. At origin, see what is the potential? It is 0 because due to negative charge, potential is negative. Due to positive charge, potential is negative. Both are at equal distances, right? Therefore, at origin, potential will be 0. So it is now 0 minus at infinity, potential is 0. That means to bring a unit positive charge, or you can say any charge from infinity up to origin slowly. Slowly means speed is very small, or you can say without any acceleration. Then no work is done by external force, right? Next, see what we have to focus. It is regarding direction of electric field on y-axis. Focus carefully on y-axis. If you remember, taking plus q and minus q as a dipole on perpendicular bisector on perpendicular bisector, field will be opposite to direction of dipole moment. Here dipole moment will be minus q2 plus q, negative x-axis, right? So on y-axis, the field will be, it is along x-axis, right? So work done, 0. Okay. Next, what about dipole moment? Dipole moment will be q into separation equal to 2d, and direction is from minus to plus, right? Means along negative x-axis, right? So it is along negative x-axis. Okay. Now see options. So coming to options, electric field at all points on x-axis has same direction. So this is wrong because in between the charges direction has changed. Next, work has to be done, and that is wrong because delta V value is 0. Okay. Electric field at all points on y-axis is along x-axis. So this is correct. Option C. Dipole moment. This is modulus value. Okay. But direction part. Direction is along negative x-axis. So only correct option is option C. Okay. See next problem. Right. Two equal point charges are fixed at x equal to minus a and x equal to plus a on x-axis. Given two equal point charges. Another point charge q is placed at the origin. The change in the electrical potential energy of q when it is displaced by a small distance x along the x-axis is approximately proportional. Given small displacement, right? So equal point charges. And this is plus q at origin. So plus minus a plus a. Asking change in electrical potential energy. Right now, see carefully. Let us make a diagram for this. So make a diagram for that. Right. Let us take at origin at origin we are keeping a charge q. At minus a comma 0 charge q, a comma 0 one more charge, that is q. Now we are displacing along the x-axis by a small distance at small displacement. Suppose it is now x. If you displace x right side, then see what about change in potential energy. So first I'm writing initially for system potential energy how much? Initially k into q square by separation is now 2a plus k into q into capital Q, separation is a, that is now okay for this pair, okay, for this pair. And for this pair, once again same. So I'm taking it into 2. Okay. This is taken for small q, capital Q, and again capital Q, small q. That's why 2 here. Right. Let us take now finally how much. Coming to this value, no change. But coming to here, K, Q, and Q, it is 1 by 1 becomes A minus X. Other becomes, it is A plus X. Right? See carefully. Between these two charges, separation is A minus X. A minus X. Between these two, separation is A plus X. Right? Now see this final value, how much? Final value K Q square by 2A. That is as usual. Now coming to the next one, K Q into Q. A plus X plus A minus X. Right? It is A plus X plus A minus X. Plus X minus X gets cancelled. Remaining is now 2A. Right? Check it once. A plus X, A minus X, 2A by it is A square minus X square. A square minus X square. This is now final value. Okay. Now we want to calculate change in potential energy. Then see what happens. Delta U value. When I'm taking difference, this value and this value both will cancel. Remaining is now only 2kq by A and this value, right? Okay, now see calculation carefully. Here what I can do is, I can take 2k q common. Remaining is now, it is 1 by A square minus X square minus 1 by A. Is it okay? It is minus 1 by A. Wait, we're having here 2A, right? Right, it is A. Okay, right. Now see what we get. 2kq and q. Remaining part A into A square. A square minus A square plus X square by see what we get now. A into A square, A into A square minus X square, right? A square gets cancelled. If you observe, A is a constant. Since X is very small, we can neglect X square when compared to A square. So remains only here A square and A, right? That means here change. Delta U is proportional to, it is X square. Okay? Because here X is very small. That means X square also very small compared to A square. That means remains only some constant into X square. Right? Now see option. So you can see here the options given. Proportional to x, x square, x cube and 1 by x. So answer is now x square. Okay, right. Now see the next problem. Right. Right. See what is given. A circular ring of radius r with a uniform positive charge density lambda per unit length is located in the yz plane with its center at the origin O. So ring is now in yz plane. A particle of mass m and positive charge q is projected from the point P, that is r root 3 comma 0 comma 0 on positive x-axis directly towards origin with the initial speed v. Find the smallest non-zero value of the speed v such that the particle does not return to P. Okay, This is the question asked in 1993 for 4 marks. See what he's asking here. Find the smallest non-zero value of speed v such that the particle does not return to p. Okay, right. See how we are starting this one. Projecting from r root 3 comma 0 comma 0. Right. Let us make a diagram for given data. Let us make a diagram for that. This is now ring, which is in YZ plane, and this is now, that is now given x-axis, right? And that is now it is x-axis. Okay, projecting from it is from a point r root 3 comma 0 comma 0. Okay, towards origin. This is origin. Now understand carefully. This charge is now positive, and this charge also positive, right? So this positive charge repels now this positive charge. When speed is given towards origin, because of the repulsive force, speed keep on decreases. And here condition is the particle should not return to the point P. Means from where we are projecting, right? This is point P. See how this is possible. If particle is able to reach origin, at origin there is no force. Okay, then there is no chance for particle to reach point P. So basic condition is that it has to reach at least origin, at least. So why I'm saying at least means if it is able to cross origin, then again because of this positive charge on the ring, repulsion will be there along negative x-axis. If the charge crosses the origin, because of this positive charge, repulsion will be there along negative x-axis. Therefore, there is no chance of coming back. So, minimum condition is at least it has to reach origin, at least. Okay. Therefore, what we can do here, this loss in kinetic energy should convert completely into this loss in kinetic energy should completely convert, or you can say it should be greater than or equal to charge into potential difference. Charge into potential difference. Okay. Now see carefully on the axis of a circular wire, potential difference potential equal to, I am writing here potential equal to, it is K Q by square root of R square plus X square, right? Okay, that is the potential on the axis of the ring. Now see here at point P potential, take X value R root 3. So it is now 3R square plus R square, 4R square. It becomes 2R, right? So it is now KQ by 2R, right? And if you take at origin, potential is, at origin means X value how much? 0. It becomes now KQ by R. Okay. So see carefully, at origin potential is maximum. Okay. So now particle is moving from low potential to high potential. Okay. That means its potential energy is now increasing. So how it is increasing means it is at the cost of the loss of kinetic energy. So kinetic energy is now decreasing, and that is now increasing the electric potential energy. Okay. Now delta V value how much? We can find there. Then half m v square or V value should be greater than or equal to 2q delta V value. Okay, first I'm taking a delta V only. Delta V by m, right? Under root means power is 1 by 2. Now substitute the values there. From these two, delta V is equal to kq by 2r. K value 1 by 4 pi epsilon naught q by 2r. Okay. See carefully, kq by 2r and kq by r. So difference how much? Kq by 2r and q value. Now substitute that in this one. 2q by m in the place of delta V, it is 1 by 4 pi epsilon naught q by 2r. Okay. Right. Now here what happens is 2 gets cancelled. It is a whole for 1 by 2. So our answer is now q and q square by 4 pi epsilon naught m r under root. Okay. That means if speed equal to this value, then it comes to rest at origin. At origin, there is no force bothering on the charge. Therefore, it won't move back. Okay. If it is greater than this value, it enters onto the negative x-axis where this charge on the wire is repelling this charge. Therefore, it moves up to infinity because of that repulsive force. So that means when they ask minimum value, it should be equal to this value, equal to. Then that comes to rest at origin. Okay. So this is our final answer. Okay. Right.